Some questions to ponder here at the end of section 4.1. If the derivative is equal to 0 or doesn't exist at an endpoint, could that value be a critical value? And the answer is no, because critical values must happen at interior points. Critical values must be at interior points. Second question. If the derivative is equal to 0, does that mean that a relative extrema must occur? If not, come up with a graphical counterexample. No. So, the derivative equals 0 means graphically that you have a horizontal tangent. But does that mean that you must be an extrema? No. Okay, I could draw the graph of x cubed, and at 0 the tangent is horizontal, but it is not an extrema. So f prime of 0 is 0, but not an extrema. Third, if the derivative is undefined, does that mean that a relative extrema must occur? Again, they're candidates, but that doesn't guarantee their existence. So if it's undefined, it's going to be a no again. That means that I had a vertical tangent. And I could draw a graph that has a vertical tangent that does not have an extrema. So at that point C, there is a vertical tangent, but no extrema. So we do have f prime of C failing to exist, but x equals C is not an extrema. So even though sometimes we could easily draw pictures where it was true, that one is a place where the derivative equals 0 and is a critical value, I could easily draw places where it was true, I am undefined to the derivative, and it is. It's also possible for it to not be a critical, where it is a critical value but is not a extrema. Okay, example 4, we're going to decide whether each of these points, A through J, is a absolute max, min, relative max, or none of these. Okay, so first of all, A. A is an endpoint. Endpoints can't be relative. Remember that relative is the same as local. So A is none. You look at the other endpoint right away. That is not the absolute highest, so it's also none. Okay, now to the interior points. Okay, I have minimums at C, F is not defined, and I. It looks like the lowest one of those is I, so that makes I an absolute min. But I is also a relative min. It's both, because it's an interior point. C is going to be a relative min. It's not absolute. Okay, now let's look for some absolute maxes, or local maxes. I have a maximum, another maximum. Those are my only two. D is the absolute tallest, so that's the absolute max. It's also a relative or local max. G is just, I keep wanting to write local, but relative. Local or relative, same thing. A relative maximum. It's not absolute. Okay. Now for the other points, they're all going to be nones. B, nothing's going special there. It is still, all of these points are first order critical values. It does have the derivative, doesn't exist right there, but it's not actually an extrema. E, the derivative is equal to 0 there, but it's not actually an extrema. F, the derivative doesn't exist there, but it's not actually an extrema because it's not continuous there. H, the derivative fails to exist there because the limit is approaching two different values, but it's not actually, even though it is a critical value, it's not actually an extrema. Okay, let's look at number 5. Sketch the graph of a continuous function f on 0, 4 that satisfies the following properties. So the derivative has to equal 0 at 1 and 2. So that means that I need something that's going to have a horizontal tangent. Okay. Then the next thing I need is that I have an absolute maximum at 1. Okay, so that one's definitely going to be a smooth maximum. I have an absolute minimum at 0, and I have a local minimum at 2. Okay. Now, because I don't have the derivative equals 0, and I don't have the derivative doesn't exist at 0, and it's absolute, that this means that this is going to have to occur at an endpoint. Otherwise, if it occurred at an interior point, the derivative would either need to be equal to 0 or fail to exist, and I don't have those two conditions. So I'm going to be the absolute smallest at the endpoint, x equals 0. So I'm going to put that down here. And I am going to be continuous, so no breaks. We're going to be smooth. So it's going to smoothly connect. It's going to smoothly connect through x equals 1. It doesn't really matter how high I go as long as I don't go any higher, because that needs to be the absolute maximum as well. Then we're going to have a local minimum at 2. And then we have to continue all the way to 4. Make sure that we don't go any higher or lower than our absolute max and our absolute min. So since our absolute max is up here, I kept the rest of my graph below it. This is my absolute min. The rest of the graph had to stay above it. This is a local min, and that is both a local and an absolute max.